minus 1 plus f. And this is very important. It is a kind of not ellipticity condition, but very close, that a of x r psi dot psi, remember it is a vector value function, is bounded by psi to the p minus dr to the p minus g. Okay, what is important here is to see that the growth of b respect to psi and respect also to r is dominated by the growth of a respect to the same variable. And it is really a sharp contrast which was developed later on. Now, the function a, b, and so on, they have to belong to some space. Okay, this looks a little technical, of course, but it will be key point. It will be very important. The value, the space to which all those coefficients belong will be very important in further application. At the time of Serene, it was just to help to have to use Hölder inequality and things like that. Now, all the solutions are understood. The solution of my equation here are understood in the weak sense. That means in at least we have that A must be to the W1 P minus 1 or W1 P log, and regularity shows that they are continuous. So what are the three targets of Jim-Savin? To study, we assume that omega is a point, contains, that omega contains the point O. The first question is about removable singularities. Under what condition a weak solution of my equation 1,1, not only in omega minus 0, but in omega minus f, where f is in general a closed subset of omega, can be extended by continuity to a solution of the same equation in all omega? First question. Second question gives the behavior near x equals 0 of singular solution of my equation 1,1 in omega minus 0. And third problem, which was studied by Jim-Savin, give condition for existence of singular solution of 1,1 with behavior which is just described above. Because these are the main problems of Savin. So what is the approach of Savin? Savin's first approach is an Harnack inequality. An Harnack inequality which we suppose that if P is between 1 and capital N, and you assume that U is a non-negative solution of my equation 1,1 in BR, then the max of U on BR is bounded by a constant times the minimum of U on the same ball BR plus some constant K. Okay, and what are C and K? Okay, C depends upon, of course, A, which is a constant, but it depends also on the value of the norm of the different coefficients B, C, and D in some LP space on B2R. The same for K. So this is the starting point of Jim-Savin. The value of the constants C and K will be fundamental in further applications. Okay, in the case now P bigger than N, this is the second type of Harnack inequality. If P is bigger than N and U is a non-negative solution in B2R, then U of X is bounded by U of R plus K times exponential of C. Okay, it's complicated. X minus Y over R to the 1 minus N over P. We will not use very much this type of inequality, but those proof of inequality, they rely on two things. That's the Moser iterative scheme. That means you multiply the equation formally by u to some power plus a cutoff function. And you have an estimate of u in L infinity in a smaller domain. Now you multiply also by u to a negative power, and then you have an estimate of u in a of the minimum of u in a also smaller domain. And you realize now those two estimates, you connect them with the John and Nirenberg lemma. Okay, consequence, a corollary, that is any weak solution of 1,1 is locally Hölder continuous. Now, if you want to study the behavior of the solution, you introduce mu p of x, which is x to the norm of x to the p minus n if p is less than n, and logarithm of 1 over x if p equal n. Okay, up to now, mu p of x is not the solution of anything for the general operator minus divergence of a of x u grade u. But of course, we know that for if, as a particular case, the operator a is just the p Laplace, then here we have the fundamental solution of the p Laplace. But up to now, they are just function of comparison. And what says the theorem of Serine? I think the most probably the most important theorem of Serine. If p is between 1 and n, if u is a solution of this equation in omega minus 0, I assume that it is bounded from below. It's not negative, because I need, of course, to use Harnack. Then, essentially, we have a almost characterization of singularity in the sense that either there exists some constant c bigger than 1, such that u of x is between c times mu p and 1 over c times mu p for a smaller ball, x between 0 and r0. Or, if you do not have this, then u can be extended by continuity as a solution. Okay, that means the case I is a full characterization of singularity, and 2I is means that we have a removable singularity. Now, this is a very important result, but which connect, of course, which is based upon the fact that A is a dominant term. Other type of results. Now, if you take, for example, A of x r psi is norm of psi to the p minus 1 times psi, then essentially here, you have here that this operator, divergence, it should be p minus 2, not p minus 1, I'm sorry. Divergence here is, it is a p Laplace operator. Okay, so replace p minus 1 by p minus 2. This is a p Laplace operator. Then what you have is, you know that the mu p are exactly the fundamental solution. And the Serine results assert that any non-negative p harmonic function in omega minus 0, either it satisfies this estimate, 1,7 here, that it between essentially u over mu p is bounded by two constants on two sides, or it is regular. Actually, with Krishnasamy, I prove that we have a much more precise result for the p harmonic function, that we prove the following in 1986, that if p is between 1 and n, and u is a non-negative p harmonic function in omega minus the origin, then either u can be extended as a regular solution, or there exists some constant positive case such that limit of u of x divided by mu p of x is equal to k. That means we have a precise result. Okay. Serine also studies the removability problem. The removability problem is in that case, for serine, it was in the following sense. You assume that F is a subset of Rn, a bounded set. You say, consider S between 1 and infinity. You define the Sobolev kind capacity C1S of F is infimum of integral over Rn of grad zeta to the S dx for all zeta which are C infinity of Rn, which are between 0 and 1 and which are equal to 1 on F. So this defines the capacity. It's a way of measuring sets. And okay, also if S is bigger than N, then we need a little more precision in order to define correctly the capacity. Okay. And so what are the results of Jim Serine? He has two types of results about removability. The first one is the following. You assume that S is between P and N, and F is a compact set with capacity 1s0, and you assume that U is a solution in omega minus F. Now, if there exists a delta positive such that U belongs to L of theta 1 plus delta, and theta is SP minus 1 over S minus P, then U can be extended as a continuous solution. Okay, this appears a very technical condition, and but for example, if S equal P, you can see that what it essentially means that if you have a bounded solution with in omega minus F, universally bounded, and the capacity, the C1P capacity of F is 0, then you can extend this solution. So this is the first type of removability result, which is based upon suitable multiplication by test function, which are defining the capacity. Okay. Now, this capacity approach, I say was used by this type of test function which defines the capacity actually. You can take, if you have a set F, you can take test functions which are C infinity in omega minus F, okay, with value between 0 and 1, and they're supposed to vanish in a neighborhood of F so that you can use them as test function. And now such that the integral of grad zeta n to the S converges to the integral of grad zeta to the S. So this is the first approach. The second approach was based upon the construction of tubular neighborhood of a smooth submanifold. You can take, imagine a smooth submanifold, then you can define a tubular neighborhood of this manifold is a set of point X such that the distance of X to F is less than some value. Okay, and this is a kind of tube around this manifold, and the volume of tube has been studied by Hermann Weyl just in the 40s. Now you assume that U of X, now you take a function F, which is a solution of 1,1, the equation in omega minus F. You assume that U of X is a capital O of the distance from X to capital F to the P minus S over P minus 1 plus delta. Delta is positive, or the capital O of logarithm of the distance of X to F to the 1 minus delta if P equal N, then you can extend the function. The important fact here is that you have the delta, and I am going to tell you why. That if F is a point, essentially it means that if U of X is a capital O of the mu P of X minus X0 to the 1 minus delta, when X goes to 0, then you can extend. But for p-harmonic function, because you have a sharp condition and comparison between solution, so this condition can be weakened in order just to have that u of x is a little o of mu p of x minus x0. You can have, of course, you cannot have something better, because the fundamental solution is really mu p of x minus x0. Okay, and the same for the function of p-harmonic function. You can extend also in order to, instead to replace this power plus delta, you can replace by a little o of the distance to the sharp condition p minus s, p minus 1, and a little o of the distance of the logarithm of the distance in the critical case. So this is just to mention, but of course, there is no comparison principle. You see, in serine, there is no comparison principle, only integration. Okay, now I'm going to see a second category. Now I'm going to go further the work of Jim Serine and to see what happened for other specific equation. And first, I will speak of semi-linear elliptic equation with an absorption. The model case is Emden-Fowler equation. Emden-Fowler equation, which is important here, is that the growth of the reaction term dominates strongly the growth of the diffusion operator. So if we go into spherical coordinates in R plus cross Sn minus 1, this is a sphere, then you have minus URR minus n minus 1 over RUR minus 1 over R square, the delta prime of U plus UQ minus 1 U is 0. Delta prime is a Laplace-Beltrami operator on Sn minus 1. Observation also is that this equation here, 2, 1, is invariant by the family of transformation TL, which are defined by TL of U applied to U at the point X is just L to the 2 over Q minus 1 U of Lx. And it's classical, it's an old result, it's a very old result that when you have an invariance by scaling transformation, then you can have, you can hope to have a separable solution. It's something which is very old. And so what are self-similar solutions? They call it also separable solutions. That are the solutions which are invariant by TL. Okay, then it's immediate that TL, if for any L, this is for any L, of course, then if U is self-similar, then U have the shape that U of R and sigma is R to the minus 2 over Q minus 1 times omega of sigma. And omega of sigma satisfies this equation on the sphere, minus delta prime of omega minus lambda and q of omega. This constant will play a very important role, plus omega q minus 1, omega is 0 on Sn minus 1. And this is the value of my constant lambda and q, 2 over q minus 1 times 2 over q minus 1 plus 2 minus n. Now, if a very important observation is that lambda and q is positive, if and only if q is between 1 and n over n minus 2. So, consequences. If q is bigger than n over n minus 2, there exists no solution except 0. Okay? If q is between 1 and n over n minus 2, there exist at least two constant solutions, plus or minus omega 0, where omega 0 is the lambda n q to the 1 over q minus 1. Now, also by the maximum principle, any solution, omega, is between omega 0 and minus omega 0. Okay? And the first statement is very easy. You just have to multiply by omega and to integrate. There is no boundary, so it's immediate. And this is just the maximum principle. You have a solution bounded. You look at the maximum of omega, and you see the minimum of omega, and you will see that it is exactly between those two constants. Now, something else is that if Q is between n plus 1 over n minus 1 and n over n minus 2, so we know that there are constant solutions, but all the solutions are constant. How do we do that? You just look at this equation here, you average it, you make the average, you make omega, and then you compute the minus delta of omega plus minus lambda n q omega minus plus omega q minus 1 omega minus the average of this, but the average of is 0, minus lambda n q of omega bar, I call it this is omega bar, plus the average of omega q minus 1 omega. I multiply by omega q minus 1 omega, and there is a miracle, then there is here a positive, in this equation, there is a positive contribution. And since omega minus omega bar has no component following the first eigenspace of the Laplace-Beltrami operator, which is a space of constant, then the contribution here is going to be bigger or equal to n minus 1 omega bar omega minus omega bar square. And this is a result. Now, if Q is between 1 and n plus 1 over n minus 1, then you can make it's easy to see that you have a solution which are bifurcating from 0. So there exists non-constant solution. Okay, so this is the structure. Okay, in the case when you have in this case, we know that there exists non-constant solution, but we don't know exactly. We don't know the structure of the set of this set. Actually, you can imagine the following things. You take a tessellation of the sphere. That means you cut the sphere in domains which are reproduced by symmetry, which are the boundary of which are great circles and which are reproduced by symmetry. Okay, each of them is called a domain of tessellation. It corresponds to a specific eigenfunction with a specific eigenvalue. So you can construct in a small domain of tessellation like that a solution of this equation, a positive solution of this equation, provided this term is large enough. And then after that, you can reproduce it by symmetry. And you have a complicated solution of this equation of the sphere with a fundamental positive domain, which is given by the fundamental domain of a tessellation of the sphere. So it proves just the complexity of this situation. Fortunately, when n equal 2, this is just an ODE, and I will speak of it, but it is much simpler in that case. So the first observation is a result that we proved with Bresis in 1981. It's a question of removability. Assume that G is a continuous function which satisfies lim inf of G of R divided by R to the n of n minus 2 is positive when R goes to infinity, and the lim sup of G of R divided by absolute value of R to the n of n minus 2 is negative when R goes to minus infinity. Then any solution of this equation in omega minus 0 can be extended by continuity as the Hölder continuous function intersect with W2Q for any Q less than infinity of the equation. This is the first removability result that we, for this type of equation. And what is the key element, the key estimate which is used, ingredient, is a Keller-Osserman inequality, which is very classical now. If Q is bigger than 1, A is positive, B is positive or 0, you assume that you have a solution U which belongs to L infinity log of omega minus the origin. You assume that the Laplacian of U belongs to L infinity log of omega minus the origin. And you take a function U, you assume that U satisfies minus Laplacian of U plus A times U to the Q less or equal to B. And this is almost everywhere on the set of point X in omega, where U of X is non-negative. Then you have an estimate from above, which is U of X is bounded by some constant sigma of NQ times 1 over A. Okay, these are the structural constant, times X to the minus 2 over Q minus 1, and plus additive term, which corresponds to the coefficient B here, which is essentially B to the A to the 1 over Q. And the proof is rather easy. It was not the initial proof of Keller and Osserman. Actually, they prove it simultaneously, both. But the proof now for this type of equation is just to consider in a small ball BR in omega minus the origin, you consider a function UR of Z is A divided by R squared minus X minus Z squared to the 2 over Q minus 1 plus B. So this is in the ball BR. So when X minus Z goes to R, this blow up, this equation, this UR of Z goes to infinity uniformly, and you just have after that to compute A and B in order UR of UR be a super solution in this ball BR, and then you have the result. Okay. Now about the classification of singularity, I give you the old story. The old story started from 1979. I think the first result I have was in 1979, and then it was the proof complete was published in 1981. And what is this? Is a theorem of classification. You assume now we are in the range of Q for which you have singularities. That means Q is between 1 on n over n minus 2. First, if U is a non-negative solution of 2, 1 in omega minus 0, then you have the following alternative. Either limit x to the 2 over Q minus 1 U of x equal omega 0, or limit x to the 2 over Q minus 1 U of x equals 0, and there exists a constant k, which is positive or 0, such that if n is bigger than 2, you have the limit of x to the n minus 2 U of x equal k, and if n equal 2, this is the limit of minus log of x to the minus 1 U of x equal k. Furthermore, a minus Laplacian of U plus UQ minus 1 U is Cn times delta k times delta 0. And if k is 0, solution is smooth. This theorem, note that the radial case of this theorem was essentially, I say essentially because the proof is not always clear to be read, is essentially proved by Fowler. It was in 1914. That means 110 years ago. And now you can check in the radial case the construction of Fowler just by using a phase plane analysis. But Fowler didn't use this at all. Okay, what are the technique of proving, the initial technique of proving this result, the classification result that I gave, which was based upon Harnack inequality, thanks to the essentially the fact that UQ minus 1, remember that UQ minus 1 is bounded by 1 over x, norm of x to the square. You have Harnack inequality for an equation that you write minus Laplacian of u plus UQ minus 1 in absolute value, but it is positive in that case, UQ minus 1 times u. Okay, so you have Harnack inequality, and Harnack inequality is very important because it shows that in some sense, the result, the solution does not oscillate too strongly on the same circle. That means the max of u of z for z equal norm of x is bounded by c times the minimum of u of z for z equal norm of x. And this is value for all x in BR over 2, minus 0, of course. This is okay. Now we use also as a primitive the first technique that I used. I have combined this Harnack inequality with the Fowler result concerning the ODE. And this is essentially showing that if you have a solution, it is between two solutions of ODE, and we know exactly that solution of the, in Fowler case, when there is a strong blow-up, then solution of the ODE behaves in the same way. This was the primitive technique. Now we have so many others. Now, second case, which corresponds to the fact that the set of solution, I call it the stationary solution. This is a set of solution of minus delta omega minus lambda nq of omega plus omega q minus 1 omega. So this is this equation of the sphere. I call this a set of stationary solution of this equation. Okay, we know that when q is between n plus 1 over n minus 1 and n over n minus 2, if you consider in the where there is a case where there is only three solutions, three stationary solutions, then you know that if you have a singular solution, not necessarily with constant sign, then the limit of x to the 2 over q minus 1 u of x exists, and it belongs to the set omega 0 minus omega 0 and 0. Oh, the theorem is also valid when q is n plus 1 over n minus 1. Okay. Now, if L equals 0, essentially, as a consequence, you know that there exists a k such that x to the n minus 2 u of x goes to k, or minus log of x to the minus 1 u of x goes to k. Okay, and you have also the equation in the sense of distribution. Now, for proving this last result, essentially, we prove it's called the isotropy. The isotropy means that you control the u minus average of u. Okay, and you introduce the norm of u minus the average of u of r in L2 of Sn minus 1. You call it x of r, and you see that it satisfies some ODE. It satisfies some ODE, and this ODE is x r plus n minus 1 over r x r minus n minus 1 over r square x. This is coming from the Laplacian. Okay, and this is bigger or equal to c times x to the q. Now you can analyze this ODE, and that you obtain that x of r is little o of r to the 1 minus n under the condition. And now this is sufficient for getting the isotropy. Okay. Now I'm going to speak of a much powerful method, which was introduced much later. And it's called the energy method. The energy method is a very powerful method with a case where it doesn't work. So what is the energy method? We use, we write the function v of t and sigma is r to the 2 over q minus 1 u of r and sigma. And t is minus logarithm of r. It's called Hamden transformation. Okay, then what is the equation which is satisfied by v? Remember, look, in our case, v is bounded because of Osserman estimate. And the t goes to plus infinity if r is between 0 and 1. Now it satisfies now this equation, minus vtt plus some important constant here, theta nq vt, minus delta prime of v minus lambda nqv plus vq minus 1 v is 0. So this theta nq is called the damping term. It is n minus q plus 1 over q minus 1. It's very easy to compute. And it vanishes if and only if q is n plus 2 over n minus 2. This is not surprising because this is the classical exponent, call it the Brojaev type, Brojaev exponent, correspond to invariance. Now, if V is bounded by standard elliptic regularity estimate, this is bounded, then we obtain that all the derivatives, in that case on the sphere, because remember that we have an equation on a cylinder, all the derivative up to some order, derivative in time and derivative in a spherical variable, are uniformly bounded, okay, in up to some exponent, okay. Now you define the notion of trajectory of V. This trajectory of V is in the space C3, for example, and I call it T plus of V is a union of the V of T dots in the space. What we know, this is a union of all those sets, and what we know that this trajectory is relatively compact in C3 of Sn minus 1. Okay. Now with that, we can define classical in dynamical system, we can define the omega limit set of this trajectory, and this is gamma plus of V is an intersection for t bigger or equal to capital T of the union of the portion of the trajectory here, starting from the point from the point T. I take the whole intersection. So this is what? This is a, okay, this is compact. This is connected. So intersection of a set of connected compact set is never empty. So by standard topology result, gamma plus of V is a non-empty connected subset and compact. Is non-empty, connected, and compact. Furthermore, the distance of the trajectory, the distance is taken in C3, of the trajectory to this limit set goes to 0 when t goes to infinity. The question is, what is gamma plus of V? And this is a key point. Now we introduce the energy function associated to my equation, which is what? Half of integral of Sn minus 1 of Vt square minus grad V prime V square, this is a covariant gradient, plus lambda nq square minus 2 over q plus 1, absolute value of the q plus 1.
Laurent?
Yes.
Maybe some slip of the pen in 214. V of tau. Yes?
Yes. What is the problem?
Formula 214. V of tau.
Yes, you take the intersection of all the, you see, here it is a portion of the trajectory starting, yes, it should be, I agree with you. It should be starting from, I agree, it should be starting from V of tau.
Yes, clear.
Okay. It is a portion of trajectory starting from tau. Okay.
Frontal.
tau, and then you can take intersection of all those portions of trajectory, the closed portion of trajectory.
Yes, of course.
I agree. Now you multiply the equation by Vt, you integrate, and then you have this fundamental energy identity, which is d over dt of E of V, and this is equal to theta nq integral of Vt square. Okay? Now, which is, of course, E of V, because of the a priori estimate we have, it's uniformly bounded. Then the damping coefficient is not zero. As a consequence, integral, say, for t plus 1 to infinity of integral of Sn minus 1 of Vt square is finite. Since we have uniform continuity, Vt goes to 0. Vt should be Vt, I'm sorry, here. Vt, not V. Vt goes to 0 as t goes to infinity. And the same now, you can differentiate the equation, you multiply by Vtt, and you use this previous estimate, and you obtain again that integral of t plus 1 to infinity of integral Sn minus 1 of Vtt square is finite. And again, in limit Vtt t in L2 is 0. Now, if you look at the equation, if you go back to the equation which is satisfied by the function V, okay, here you see this term goes to 0, this term goes to 0. So any element in the limit set satisfies the stationary equation. Well, the question now is to identify the limit set, but in the case of theorem, when if omega is positive, or if q is between n plus 1 of n minus 1 of n minus 2, you know that the set of solution is discrete. So, okay, so in that case, you know that the solution will converge to one of the set, or one of the elements. Okay. Now, problem. What happened is the set of solution of 2, 1 is not discrete. This is a bit complicated, and this has only been completely solved in the case n equal 2. Well, first, that the solution of the equation are very simple. They are just this type of minus omega double prime minus 2 vacuum minus square plus omega q minus omega is 0. Okay? And you know that if q is between 1 and 3, this set is discrete. This set is not. I'm sorry, it's not discrete. Well, it's very easy to see that you are this. You can completely see you have the two constants, and then you have also solution which have anti-period pi. Then you have also solution which have anti-period pi over k, which has look like sine of function. You have, and then you can rotate them. That means the set of solution of this equation is topologically is a union of circle. It's a union of circle. It's because all solution can be from one solution. You can after that add constant, and then you are going to add on this circle. Also, it's noticeable, and it has some application that all those set of connected solution on a circle, the energy is constant, and all the level of energy are different, called quantization. Okay? What we prove with Matano, we prove with Matano the following result. If n equal 2 and q is between 1 and 3, and you assume that a solution, you have a solution in omega minus 0, then either there exists a particular pi over k anti-periodic solution. That means that may look like a sine, okay, of the anti-periodic solution omega, such that r to the 2 over q minus 1 u of r and sigma goes to this precise solution when r goes to 0, or r to the 2 over q minus 1 u of r goes to 0. In that case, we have to distinguish if 2 over q minus 1 is not an integer, then you have a called a weak type singularities. That means you take any there exists some integer between 1 and the absolute value of the integer part of 2 over q minus 1, and such that r to the key u of r goes to a times sine of sigma plus phi. Phi is just a change of phase. Okay, and finally, if a is 0, then u is a smooth. Okay, we can also have, in that case, of course, if k is 0, you can also have u of x, of a log of x goes to a. Okay, goes to the weak type of singularity. Now, the case where 2 over q minus 1 omega, 2 over q minus 1 is an integer, is still open. Okay, I'm not going to detail completely the proof. The proof is essentially a proof in a Matano style. That means to try to see the oscillation of the change of sign, the number of change of sign of function, the number of change of sign of function, and this has been developed by Hiroshi Matano since the beginning of the 17th. So we have adapted it to the case of the elliptic equation. I will not. So I don't. It's a question of difficult. So if I will send maybe my slide so that you can see. Now, interesting is a case where what happens. This is a very useful technique if the limit is 0. If r to the 2 over q minus 1, u of r goes to 0, that means if v goes to 0. So, which is important if we want after we do not have a strong singularity, and we would like to prove that we have a weak singularity. But it is difficult to start actually the kind of descent. And we have a lemma, it's called the eta function, that it's kind of pseudo-linearization. You take rho to be a continuous positive function defined in 0 infinity. It satisfies lim of rho of t is 0. You assume that for any epsilon positive, lim sup of e to the epsilon t rho of t is infinity. Okay? Then you can find a function eta, which is c infinity, which is positive, decreasing, goes to 0 at infinity. The lim sup of rho divided by eta is finite. That means in some sense it's close to rho. And after that, you have a series of estimates. E to the epsilon t eta goes to infinity, like for rho. And after that, you have some integrability conditions, which are detailed here. So I will not go. But how to use this function? So the problem is to start the decay. And this is called the linearization. That if q is, and this is valid in any dimension actually. If 2 over q minus 1 is not an integer, and u is a solution of my equation minus Laplacian of u plus omega q minus 1 omega is 0, such that u x to the 2 over q minus 1 u of x goes to 0, then either there exists an integer between n minus 1 and 2 over q minus 1, and a non-zero spherical harmonic function phi, such that limit x to 0 of r of k, u of r goes to phi. Okay, now we can also have either there exists a non-zero real number k, such that u of r divided by mu2 of r goes to k, or the singularity is removable. Okay, so actually the theorem that we have with Matano is actually valid. The proof is the same. In that case, we do not have the technique of Matano of separation of domain and Jordan curve theorem, and we just have this type of estimate. And the type of proof is essentially what is important is to prove that we can start the descent. Actually, we know that x 2 over q minus 1 u of x goes to 0, but actually we can have with a little, we have a little exponential descent. That means the following, and we prove that you assume that we cannot find such an epsilon, and we use eta function. We use the eta function defining for the function rho the norm of v of t in infinity. And I said now w of t is v of t divided by eta of t. So it's essentially this is bounded, w of t is bounded, and it satisfies this equation. Of course, it's a little more complicated, but which is important that this term is integrable, this term also, and this one here. So those terms are, because of the assumption we have the construction of eta, those terms are not important. And now we know that also that eta goes to 0. So you see that the limit problem here, it's a problem where there is no more nonlinearity, and it is exactly, you see that the limit problem here, when you go to the infinity, this goes to 0, this goes to 0, this goes to 0, 0, 0. So we have lambda n q of omega plus delta prime of omega is 0. Okay, but it doesn't work. And omega is not 0 because of the assumption. But it doesn't work if lambda n q is not an eigenvalue of the Laplacian on the Laplace-Beltrami, and this is exactly the condition. So after we have this, we start the fact that we can go below and below and below. Okay, this is the starting point. After we have a small exponential decay, it is a standard, I say, Fourier analysis of harmonic analysis to show that by projection of the eigenspace of the Laplace-Beltrami operator that we have the real result. Okay. Okay, I can just mention some result, extension of the result on removability that I have also proved. You can extend this the result of we extend actually the result of Bresis in the case then the singular set is a compact d-dimensional submanifold. And it's the same type of, you replace the dimension by the codimension. Okay, the codimension of 0 is n. The codimension here on the sphere here, it is n. It's n minus d. Okay, and I will not go very far. I would like also to mention a last result due to Barras and Pierre. Oh, how many time I have? Okay. Oh, you hear me?
You have about 3 minutes.
3 minutes. Oh, it's too much. Too much.
Even too much. Okay, you can take more.
No, I don't want. Okay, I would like to finish this small chapter about semi-linear equation with absorption.
Laurent, be quiet, because we have 20 minutes till next speaker.
Okay, no problem. So I will. But essentially, I have almost.
You're free. All is okay.
Okay.
Please, very interesting.
Okay, so the first method, I say the first method, what if first extension of tubular removability was to, in some sense, construct tubular neighborhood around the singularity. Actually, with Bresis, what we proved, our technique was essentially to construct a tubular neighborhood of the singular point. But the tubular neighborhood of a point, it's a ball. In that case, and this is the key. It was a key point with Bresis. So the idea after that I've extended it to general set, and with a compact set you can construct the tubular neighborhood. You have the a priori estimate, and then you can prove the result. Essentially, the main point is to prove that the nonlinearity is integrable. Okay, and after that, after it is integrable, then the remaining is easy to prove. Okay, so this is the same type of construction. You see here, it is the estimate. We have the Keller-Osserman estimate in our case. It reads like that. Now, the second method, it's a very powerful method, which is due to Barras and Pierre, is clearly for this semi-linear equation with absorption. It is more powerful, but I will say something after that. Essentially, it's more general in the sense that it is a capacitary condition, and it uses capacity, the not T1P capacity, C1S capacity, as in the result of Jim Serrin, but C2 capacity, to something capacity. This is the C2 Q prime capacity. Q prime is Q over Q minus 1. And the result of Barras and Pierre, it is from 1984, is says that if you have a compact subset, there is no regularity. If you have a compact subset of omega with C2 Q prime capacity 0, and if you have a function g which satisfies lim int of g of r over r to the q positive at infinity, and lim sub g of r divided by absolute value of r to the q at minus infinity is negative, then you can extend the solution. You can extend the solution. And so this is a, so for this type of equation, this is more powerful. However, if you compare those two results, for semi-linear equations, the result of Barras and Pierre is much more powerful, but you cannot use it at all for equation like minus Laplacian of u plus g of x u grad u is 0, because there is no duality here in some sense. In some sense, for this type of operator, and that we have studied also, and in particular, if the growth of g is a power, so the construction of tubular neighborhood is more efficient. Okay, now I'm going just to speak about some extension, which are very important. One, the extension of equation with semi-linear equation with RD potential. A typical example is minus delta u minus mu over x square. The x square should be outside, plus u q minus n u is 0. Okay, and there is a condition which is mu has to be a real number, and usually it assumes that mu is less or equal to mu 0, which is n minus 2 over 2 square. Okay, the first study was done by, I've done with my student, Gersh, and it was published in 1991, and it was very close to what we did. And a very general generalization has been done by Sirchtea, and who provide a complete classification of the isolated singularities for nonlinear equation with inverse square potential, with very general nonlinearity, with power and something. And so I think she has many papers. One of them, very important one, is the one which appears as a memoir of the American Mathematical Society. And I think she will speak of many problems, many aspects of this problem, which is an extremely rich problem, actually. Just an observation about the, if you look for separable solution of this equation here, look at this, you know that you have the a priori estimate of Keller-Osserman, so it's not a problem. So you have the a priori estimate, you can say, well, why not try to see separable solution? Then you can find separation solutions which are under this form. Lambda n q is mu plus lambda n q to the 1 over q minus 1. Of course, this is valid if this is non-negative. Okay. Interesting case is a case where q is n plus 2 over n minus 2. Okay. So in that case, which is very funny, is that in that case, you have this type of estimate, okay? If you look at separable solution for mu bigger than mu 0, you can look at what is lambda n plus 2 over n minus 2 and mu. This is a mu, this is the term here. So it is mu minus mu 0 to n minus 2 over 4. And you have this equation here. So this equation is interesting because there is no damping term. There is no damping term, and there is conservation of energy. there is conservation of energy, and Liqua proved in 1995 that even if there is no conservation of energy, so you cannot use the energy method. There is conservation of energy because the damping term is 0. Here there is no coefficient of Vt. So there is conservation of energy. So in that case, you can estimate there is no reason that Vt goes to 0. But actually it is. It is, and you have the existence of a solution. You have existence of a solution. Take a solution of this equation here. This equation here, and you know that in that case it is proved that V of t goes to minus mu minus mu 0 to the n minus 2 over 2 when 2 goes to infinity. Now, which is also interesting, so you have mu minus mu 0 to the power n minus 2 over 4 is a particular solution of this equation, the stationary solution here. Okay, and actually, there exists is called a connecting orbit, which goes to minus mu 0 to the n minus 2 over 4 to mu minus mu 0 to the n minus 2 over 4. That means it's a solution which is defined on R cross Sn minus 1, such that limit at minus infinity is minus mu 0 to the n minus 2 over 4, and at plus infinity is mu 0 to the n minus 2 over 4. So there is, and even if there is no waste of energy, there is a connecting orbit. This is something which is a bit strange for me. Okay, and just to say a small word, you look at the ODE here. If there is no diffusion, you have this ODE. So this ODE is very simple to treat because if you multiply it by Vt, you have a conservation of energy. You have conservation of energy, so you can see exactly what are the curves. What are the curves of for the solution which is independent of the sigma variable. But in the case of a function which depends on sigma, well, the conservation of energy says just that you have, in the space of infinite dimension, you have just the solution are located on a submanifold of dimension 1. So it's not enough, of course. Alors, I made some computation at the time to see what exactly is the meaning. If you want to mimic some very simple, you replace the Laplacian by a matrix. You replace the Laplacian by a matrix, and you look at the equation as a second order equation. And in the case, if you look at the equation corresponding to this, replace just Laplacian by a very simple matrix, 1 minus 1 minus 1 minus 1. In that case, 1 minus 1 minus 1, 1. In that case, you have a very chaotic, totally chaotic behavior. And on the contrary, this is just to say that this is not very surprising. If you replace now by this, the u double prime, and you here by minus u double prime, so in some sense, this is an hyperbolic equation. So you see that in that case, the solutions are almost periodic.
Laurent, excuse me.
Yes, this is the end.
It remains only 3 minutes till next lecture.
Okay.
Very interesting, but
I have finished.
Yes.
I have finished. I'm sorry.
Thank you.
Okay. I think I'm good because I'm 37 page over 79.
Maybe we'll continue tomorrow because it is. You will have the lecture tomorrow. And
yes. Well, tomorrow, I will. You see, tomorrow it will be. I have finished with absorption. Now tomorrow will be equation with soup.
Yes.
And this
maybe
is
some question. Maybe some our audience would like to ask you something.
Of course.
Yes, in written form, please.
There is another possibility. Colleagues, please raise your hand if you want to ask something.
Some questions.
Откуда такой резонанс? Well, we've seen questions, neither in the written form, no raised hands. Maybe our listeners would prefer to ask questions after the second lecture of Professor Veron, in order to have the whole understanding, and probably this is the case. And thank you very much, Professor Veron. Now, please.
Now it remains only 1 minute till the next.
I'm
talk.
sorry.
I would like to ask. Well, Laurent, we don't say bye. Of course, we will continue tomorrow. Very interesting talk. Yes. You gave very interesting talk, and I hope tomorrow we continue this very good discussion.
You know,
but we have to follow to our schedule. And
yes.
Now it remains.
You know, Andrei, I
Yes.
can send. I will send the. Well, I think I already sent the slides. So I think if the people want, that they can.
Very nice. I planned to propose to send me the slides, and I will send them if somebody will ask us.
Yes, I will send you. Okay, no problem.
Yes, of course.
Okay, thank you.
In general, I thank you very much for this very interesting talk today.
Thank you.
So,
thank you.
But now I would like to invite Professor Yun Chen Wei to prepare his presentation and to start.